following MOLA, in some ways we were in demand to consider whether we could provide a laser altimeter to another mission.
A few missions, actually. It was no longer a question of if LiDAR could work, but where else it could work. But as the opportunities to test the limits of LiDAR arose, so did the challenges ahead. The Goddard team quickly began to see the evolution of LiDAR missions, building on the successes of new frontiers mapped by MOLA.
We've measured the changes, the seasonal changes in the Mars ice caps, both the North Pole and the South Pole. We've measured the volumes, we've measured the mass that's involved in that. We now have a density. So now we know the kind of processes that are taking...
Dave Smith invited me to be on the MOLA altimetry science team. And that was because of my experience with using altimetry over land rather than ocean processes.
Zwally was an obvious choice to study the Martian ice caps for MOLA, given his decades of expertise with our own polar regions, studying the ice sheets of Greenland and Antarctica through the 1970s and 80s.
And then as we went into the 80s, NASA was sort of the beginning of the development of the Earth observations program.
So the Earth observing system, I think, will be the first effort targeted at looking at the whole Earth system as a system, rather than just the little components that make it up.
Somewhere along then, I teamed up with Jim Abshar.
Jay had been pushing for a long time for a dedicated ice altimetry mission, which turned into ISAT-1.
Designing ISAT-1 marked a major leap in what LiDAR needed to do and how challenging it would be to do it. To measure the changing ice sheets, the LiDAR had to be far more precise, cover the same tracks season to season, and it needed more power and a larger instrument, which meant much more time to build.
We built a simulator for ISAT-1 that allowed us to sort of figure out how precise it could be, how we would process the waveform data coming back, how we would track the surface.
This algorithm was much more complicated than anything I had ever worked on before.
But all this meant essentially for the ISAT mission, you needed a much more advanced version of MOLA.
In Mars, we really didn't know what was there until we got the measurements, so we were doing discovery. On Earth, we have to make quantitative measurements about what's happening.
4, 3, 2, 1. And we have ignition and liftoff of NASA's ISAT and ChipSat spacecraft looking at stars and ice.
But after, we'd worked on glass at that point more than a decade, and it already launched, and usually you think, okay, now we're going to be able to enjoy the data coming down, and what can we see in the data? But there was much more, what is this mystery we're seeing? Why is the laser energy going down? Things were not working the way we expected them to, and there were mysteries, and we weren't expecting, after MOLA in particular, to have mysteries at that point.
One of these unexpected mysteries came down to the wire. Several wires, actually.
What happened on glass was the laser diodes had gold bond wires and indium solder. If you bring these two metals together, even though they're not reactive, they do combine to form gold indide.
The gold indide ate away at the wires, leading to added thermal stress, and eventually the failure of the first laser. And the second and third lasers were degrading as well. Tough decisions were ahead.
When these missions operate, there's a lot riding on the missions. You don't want to make any mistakes. You want to optimize things as best you can.
The question was, given that we would have so much lifetime expectancy from the lasers, well, the scientific decision was that the best way to use that was to operate for periods of about a month and do that 3 times a year.
That decision paid off when ISAT showed dramatic change in land ice around Greenland, and it also proved that LiDAR could be used to measure something called sea ice freeboard, a major breakthrough in determining sea ice thickness and an essential science goal for the future of ice measuring satellites.
Even though the ISAT project required much more care and feeding, it really laid the groundwork for all the subsequent missions that Goddard has flown.
Around the same time that ISAT was developed, Goddard was tasked with designing a laser for measuring a place far from any icy poles.
Sean Solomons was the PI of Messenger, and he said, I've been asked to PI a mission to Mercury. I really want a laser altimeter on board. Can you make one that will work there? So the short answer seemed to be, yeah, I don't see why not, but there will be extreme thermal circumstances that we'd have to worry about.
That was a really tough one because you fly in close to the 800-degree planet, and then you have a 12-hour orbit.
The temperature changes by tens of degrees in a few minutes.
It had to always shield itself from the sun constantly, which meant that in orbit it was often at a very high angle. It was a challenge to try to continually figure out where the surface of Mercury was.
And then they wanted it to be small, much smaller than MOLA. I think it's ended up to a quarter or a fifth of the size.
But I remember the manager who was running it for us at the time kind of said, you realize I've thinned every wire in this electronic package so thin that you better not look at it twice because it might break. But that's the level we had to go to get within the 7 kilograms, okay? And MLA was the laser altimeter that we proposed, and this was really pushed the limits of what we could reasonably expect to do.
Despite the extreme environmental gauntlet, the Mercury laser altimeter kept on collecting data for 4 years, right up until the very end when Messenger crashed into Mercury in 2015. But before that, it captured historic views of the planet's topography.
It is time for America to take the next steps. Beginning no later than 2008, we will send a series of robotic missions to the lunar surface to research and prepare for future human exploration.
And then one day, the president, I think it was George Bush, suddenly decided we're going to go back to the moon. Wow, all of a sudden, okay?
We've been thinking about putting a LiDAR around the moon for a long time, actually.
And I really wanted to have a crack at doing a good one instrument for the moon. I mean, my interest was in gravity and topography, two things that need to come together to measure the structure of a planet.
And then all of a sudden, we got a call from headquarters. Can you design a LiDAR around the moon, to map the topography?
And so the instruments were chosen from proposals based on the ability to help select sites and determine the safety of landing in particular sites on the moon.
The LiDAR would be the Lunar Orbiter Laser Altimeter, or LOLA, and it marked another leap into laser altimetry.
We also came up with the idea of having multiple beams.
We managed to put 5 beams on the surface, and that kind of changed the observational strategy, if you know what I mean, of 5 parallel beams.
But after launch, Lola was suspiciously silent.
When Lola started, I think that was just devastating.
We didn't get any measurement at nighttime when we first turned on. It was quite a shock, and it was the first LiDAR that didn't work at the initial turn on.
The people that are heavily involved in the instrument development, you're pulled back in if there's surprises that occur.
On Lola, the blankets were all tied tightly to the beam expander and the telescope, and this germanium black kapton, which we didn't test with, was very strong.
And then we caused a misalignment.
I remember we discussed whether we wanted to check the alignment at spacecraft level, and we just decided not to do it. I think that was my fault, because we could have. We started in the worst possible orbit for that failure mechanism, and so we were out of alignment, and we had no signal at all, and that was just it was a tough couple of weeks.
Yeah, it is a lessons learned for life for me.
A couple of weeks later, we noticed a little blip at the South Pole, and so we had some hope. And it eventually just, as the orbit progressed, the signal kept getting stronger and stronger on the daylight side.
Despite a bumpy start, in time, Lola and the Lunar Reconnaissance Orbiter mission became revolutionary in mapping our moon.
And it turned out to be exceptional in terms of describing the topography of the moon. as a result of LOLA, I think largely, if not the others as well, the doubts about whether a laser altimeter, for example, could last, age limits, lifetime limits on the laser altimeter were dispelled.
The shape of what we build, live, work, study, operate on, whether it be on the Earth, the Moon, Mars, wherever we're going, matters.